Thank you for being part of lecture number 11, Eigenvectors. We have covered eigenvalues in lecture number 10. We'll briefly go over it and move on to our eigenvectors because they go together. Just in case you forgot any of it, we'll just briefly go over it. 4. A solution of an eigenvector is not equal to 0. The matrix A minus lambda I must be linearly dependent. This is the A matrix that we had before, our A minus our lambda I. Okay, this was our determinant. We take the determinant of that. When we take the determinant, we're multiplying 5 minus lambda times 2 minus lambda minus 2 minus 2. Then we get 6 minus 7 lambda plus lambda squared. This is called our characteristic equation so that we can solve for the roots. Once we have that, we can solve using quadratic formula or any method that you have in mind. And we can find out that lambda 1 is 1, lambda 2 is 6. The next thing we'd like to do is plug in our lambda values into the equation. And when we plug them into the equation, we get, for lambda equal 1, we get 4x minus 2y equals 0, and we get minus 2x plus y equals 0. Then when we plug in for lambda equals 6, we get minus x minus 2y equals 0, and we get minus 2x minus 4y equals 0. Then we're able to choose pick any point across these vectors that will satisfy the equation. And so we'll pick, we go over 1 in x and up for 2 in y. We see that correlates with our v1. We see our v2, we go over 2 and we go up 1, and we see that correlates with that line, with that equation. So we're able to use those. Customarily, we choose unit vectors. So to do that, we need to find the magnitude of the vectors. And we see this is a 2 and a 2, this is a 2 and a 2, so it's just 2 squared plus 1 squared, which gives you your 5. Square root of 5 for each of your values for your v1 and your v2. So that was a brief summary. Now we're going to go through an entirely different example. And our goal is to find the eigenvalue and eigenvector. This is our A matrix. With our A matrix, we now can derive our A minus I lambda, which we have here. Now the first thing we would like to do is take the determinant. The determinant of this is we take 2 minus lambda, that quantity times this mini matrix here. Okay, as you look here, you can see that mini matrix here. Then we subtract 2, and then we have our next mini matrix. We wipe out the second column and the first row. Okay, and that gives us these values. Then we use our minus 3, and then we have this block of mini matrix. At that point, we just now continue to multiply as we go through each line. We'll let you go through each line to verify your calculations. And what we find out is that we have 3 roots. Lambda equals 5, lambda equals minus 3, and lambda equals minus 3. So we have minus 3 twice. It's called the degenerate eigenvalue. Okay, so now we're plugging in to eigenvalues to get the eigenvector of the matrix. Okay, let's allow lambda to equal 5. Then A minus I lambda is equal to this new matrix. And we have this matrix right here. When we add a -2 to a -5, we get a -7. When we add a 1 to a -5, we get a -4, and we have a -5. All the other components that are off the diagonal do not change. Okay, so the first thing we would like to do is we would like to take 7 times row 3, okay, and we're going to subtract that from row 1. So if you multiply 7 times a -1, okay, 7 times a -1, so you'll get a -7 times -1 gives you a positive, and this gives you 0. And we'll be able to show you that. Okay, that'll give us our 0. We can also go through the R2 plus the 2 times R3. Okay, so we have our R2 which should be here. Our R2 plus our R3. So that'll give you what? A positive 2. A negative 2, and this is a positive 2, and this will give you another 0. Okay, so we have our 2 zeros here. And as you continue on, if you look at 3 also, 2, this is going to be, these will add up to -8. So these will be the next steps that we'll take. Okay, just follow the steps. I'm not going to go through every little detail in this. And we're going to take row 1, divide by 16, so that we can get a 1 here, and then we'll get a 2 here. Then if we divide by a -8 on 2, row 2, we'll get a 1 here and a 2 here. And then if we do the same thing for negative R3, we'll change all of that to positive. Okay, so you'll see here that we have these as zeros, and then you can look and see that these two are basically the same. So if you add these two rows together, you get 0. And then if you take row number 2 and you multiply it by 2 and you subtract it from R3, you'll get 1, 0, 1, 0. So our new equation that we're going to have is that y plus 2z equals 0, and we have x plus z equals 0. Okay, we'll use those as our main equation. Okay, so let z equal -1, then x equals 1, and y equals 2. And here is x as 1, y as 2, and z as -1. And this is the eigenvector for our eigenvalue of 5. Okay, now for our eigenvalue of a -3, we can leave off the 0 columns to save room on our paper, on our program. So we have A minus I lambda. We are plugging in minus 3, as you can see. These are all minuses, so they turn to pluses. Okay, so everything changes. The only thing changes is the diagonal, nothing else. Okay, so with this, we can take row 2, we multiply row 1 by a negative 2. And then this here will cancel out and give you your 0. This here will cancel out and give you another 0. If you look a little closer, you'll see that row 3 and row 2 are just negative of each other. You add them together and you get 0. As you can see also, row number 1 and 2 are just a multiple of 2. So our final equation will be x plus 2y minus 3z equals 0. Okay, let us take x to equal 1 and y to equal 1, then z equals 1. The eigenvector for lambda equal a minus 3, we have 1, 1, 1. Okay, so we now figured out our eigenvalues and our eigenvectors. Now that we have two of the same root, as I mentioned, it is called the degenerate eigenvalue. Since lambda sub 3 equals minus 3 as well, they're both, we have a double root in one spot, it also lies in the plane of x plus 2y minus 3z equals 0. This duplicate eigenvector is called a degenerate eigenvalue. This duplicate eigenvalue is called a degenerate eigenvalue. And the plane in which they lie is called the degenerate subspace. Any two linearly dependent vectors in the degenerate subspace can be our eigenvectors. For example, 0, 3, 2. Also satisfied as the equation plane, and it is dependent on V2 equals 1, 1, 1. So we can let V3 equal 0, 3, 2. However, it is frequently convenient to have orthogonal or perpendicular eigenvectors. In this case, we can get them by using Gram-Schmidt method. Okay, subtract part of 0, 3, 2. That is parallel to 1, 1, 1 to get a new vector, which is orthogonal to 1, 1, 1. Now, note regarding the example on page 153 of the book, they used the cross product of V1 and V2 to find V3. Do not do this. It only works for a very specific case, a symmetric 3 by 3 matrix, which the book mentioned very briefly on page 152. Gram-Schmidt's method always works. In this example, our matrix is not symmetric. So the resultant of V1 cross V2 gives us a vector that does not even lie in the degenerate subspace, whereas it is not in the plane of x plus 2y minus 3z equals 0. Okay, so we know we're going to use these two vectors that we have. And so the first one is for us to be able to find E1. We have to take the vector and divide it by its magnitude. And so the first one is 1, 1, 1. So it's the square root of 3 is the magnitude. So it's 1, 1, 1 divided by the square root of 3. So now we take y2. That's a little more difficult to calculate, but we'll try to calculate it with you. So we're going to multiply our E1, which is 1, 1, 1 over square root of 3, times our x2, which is 0, 3, 2. Multiply these two together in the parentheses, then we multiply it again, times E2. As we can see here, when we multiply this, we get 2 of the square roots of 3's multiplied times each other, which gives us the square root, which gives us 1 over 3, the square roots of 3 times each other. And we multiply this out, 0, we get 0, 3, 2. Now we got to find a common denominator, which is going to be the 1/3. Both of them if we're going to subtract them. Okay, so if we multiply this times 3 over 3, we get 0, 9, 6 divided by 3. So now we can subtract these two. Get 0, we get 6, and we get 4. All divided by what? 1/3. Okay. Now that we're finished finding and using the common denominator, now we know what y2 is. But we need to find out what the absolute value is. So if we take 6 squared and 4 squared, square root of that, the 1/3, we find out that this is 36 plus 16, square root of that, 52, and we know that 4 times 13 equals 52. So we're able to pull out a 2, because that's 4, 2 times 2. Okay, so now we have our E2, which is our y2 over the absolute value of y2, which is 2/3. As we can see here, 6, 4 over 13, and we have 3 times, notice the pattern here, this is only a multiple of what? Of our x2, okay, and that was 0, 3, 2. Okay, so we'd like for you to work on 2 more problems, your practice problem, E1, and your practice problem 2. We will post those at the end of class. Thank you, and have a nice day, and enjoy your study.